My name is Dr. Esther Trufan, and in this video, we're going to explore the reaction between Alka-Seltzer tablets and vinegar. Now, this reaction automatically implies that when we look at the composition of Alka-Seltzer, there is something that is still available to react with vinegar. So if we look at the composition of the tablet, we can easily jump to conclusions. The first ingredient is aspirin. This is an organic compound that is not soluble in water. So if you plop your Alka-Seltzer tablet in water, you will see this whitish residue that is floating around for a little bit. That is your aspirin. Sodium bicarbonate, or commonly known as baking soda, is a slightly basic compound. And it makes sense that it is part of the Alka-Seltzer tablet because this is the part that will help neutralize stomach acids. And then finally, there is citric acid as a component of Alka-Seltzer. When Alka-Seltzer tablets are added to a vinegar solution, then there are two things that are happening. There is the sodium bicarbonate that is a base, and then on the other hand, we have citric acid and acetic acid now from the vinegar that are both ready and available to react with the base. So then there are two equations that are always happening. The one with citric acid is the same one that happens in water. We take sodium bicarbonate, this is soluble in water, and we add it to citric acid. This is aqueous, and the product will be the sodium citrate. Sodium citrate has 3 carboxylate units now. It will also produce water in the liquid phase because it is happening at room temperature, and carbon dioxide, and that is in the gas phase at room temperature. To balance the equation, we will add a 3 in front of the sodium bicarbonate, a 3 in front of the water, and a 3 in front of the carbon dioxide. This is what would happen if we only added water to the Alka-Seltzer tablet. But that's not the only thing that's in our solution now. When there is vinegar available, then the base that is still in solution has additional opportunities to react. And that is the second part of this equation. Sodium bicarbonate, which is soluble in water, will react with acetic acid, or I can rewrite this COOH to the same format that we have for the citric acid. There is a doubly bound oxygen and there is an OH. That hydrogen from the OH is going to be switched out with the sodium in this double displacement process or acid-base neutralization reaction. The acetic acid is also soluble in water. It produces sodium acetate, which is an ionic compound that is also soluble in water. And just like before, it will produce water in the liquid phase and carbon dioxide in the gas phase. In this case, because there was only one carboxylic acid group on the acetic acid, it means that there is only need for 1 mole of sodium bicarbonate to react with 1 mole of acetic acid. And that will produce 1 mole of sodium acetate, 1 mole of water, and 1 mole of carbon dioxide. If we get this data set, there are a couple things that will right away stand out to us. If we plot the volume of vinegar versus the mass of carbon dioxide produced, then we see that initially we have this almost linear increase in our numbers. And that means that the more vinegar we add, the more carbon dioxide we can produce. And that means that among the Alka-Seltzer ingredients, the sodium bicarbonate is still available to react with the vinegar that is being added in addition to the citric acid. So if we are to use this data and this plot and derive a conclusion about what is the limiting reactant in the Alka-Seltzer tablet's reaction with water, then it's going to be very clear that the citric acid is our limiting reactant, and there is sodium bicarbonate still left over to react with the acid that is being added. If the sodium bicarbonate was the limiting reactant, then it shouldn't matter how much vinegar we are adding, the mass of carbon dioxide that is the result of that should not change. So if in the case of the Alka-Seltzer tablet, initially the limiting reactant was the citric acid and the access reactant was sodium bicarbonate, then with continual addition of the acetic acid, we should be able to establish at what point the sodium bicarbonate became the limiting reactant. And if we look at the data, we have this region where there's almost a linear correspondence between the volume of the vinegar that was added and the mass of the carbon dioxide that was evaporated in the experiment. And that means that this linear relationship is going to be the same as what we have if we were to do the calculations to connect the volume and then moles of vinegar to the mass and moles of carbon dioxide that are produced. After all the sodium bicarbonate is consumed, there should be a leveling off. And that's about there. If there is no more sodium bicarbonate to react with, the reaction stops regardless of how much acetic acid there still is left over to react with it. And we can easily tell if we simply test the pH of our solution, and we're going to see increasing acidity or decreasing pH with excess amounts of acetic acid being added. So where the two lines meet is the point at which the sodium bicarbonate became our limiting reactant. But that number is essentially the same within statistical differences as what we have right here when we added the excess amounts of acetic acid. From these numbers, we should be able to determine the mass of the sodium bicarbonate in the Alka-Seltzer tablets. We simply start with the mass of carbon dioxide, and we can use it at each step, or we can calculate a statistical average of the steps that are after the sodium bicarbonate became the limiting reactant. I am going to do it at each step. So I will demonstrate how to do it at the step at which we added 15 milliliters of vinegar to our solution, and it produced 0.91 grams of the carbon dioxide. We start with what we know, and that is 0.91 grams of carbon dioxide. In step 1, we convert this to moles. 1 mole of carbon dioxide weighs 44.01 grams of carbon dioxide. In the next step, we're going to convert from moles of carbon dioxide to moles of sodium bicarbonate. This is a 1-to-1 conversion. Even when there was citric acid present, for every 1 mole of sodium bicarbonate, there was 1 mole of carbon dioxide forming, because the sodium bicarbonate will react with 1 hydrogen from the carboxylic acid group. And then, because we're asked for mass of sodium bicarbonate, we're going to convert from moles of sodium bicarbonate to grams of sodium bicarbonate. And we have 84.007 grams. Upon completion of this calculation, we will find that there were 1.74 grams of sodium bicarbonate in this Alka-Seltzer tablet that had 2.65 grams as its mass. Another calculation that can easily be completed is determining the percent composition of the Alka-Seltzer tablet. If we know how much of the sodium bicarbonate there was, then it should be fairly straightforward to determine what percentage of the Alka-Seltzer tablet is the sodium bicarbonate. The calculation starts with a percent sodium bicarbonate equals, we start with the mass of the part, and that is 1.74 grams of sodium bicarbonate. And we divide by the mass of the whole, which in this case is our Alka-Seltzer tablet. At the point where we added 15 milliliters of acetic acid, the mass of our tablet was 2.65 grams. This was our tablet. And because we're calculating percent composition, we multiply by 100%, giving us 65.6%, telling us that in this Alka-Seltzer tablet, we have 65.6% sodium bicarbonate. The additional components will be citric acid, aspirin, and whatever other inactive ingredients there are to ensure the same consistent Alka-Seltzer tablet.